First, the British Prime Minister, Boris Johnson, announced an indefinite moratorium this week on mining of shale gas by hydraulic fracturing, aka fracking, citing fears of earthquakes and seismic activity caused by fracking in the past. In August this year, a 2.9 magnitude quake was recorded at the Preston New Road fracking site in Lancashire, which prompted an immediate shutdown as required by the strict protocols that we have in place. Fracking does not currently contribute to energy generation in the UK, though Boris Johnson had previously enthusiastically committed to it as a gas mining technology, but we do import more than half of the natural gas that we burn, and some of that is from fracking. As ever, this is a complex and emotive political question that is rooted in science, and it's our job to try and understand that science. James Verdon is a geophysicist at Bristol University, and he's also the co-author of one of the Oil and Gas Authority studies on the Preston New Road site that was published earlier this week. We start with the basics, and I asked James how fracking works.
Fracking works by pumping pressurised fluid, typically water, into the subsurface. The pressure in the water creates and forces apart fractures within what we call tight rocks, so rocks with a relatively low permeability, but that still contain often quite appreciable levels of gas. And the formation of these fractures allows the gas to flow from the rock into the well to then be produced. One of the biggest kind of misconceptions about fracking or hydraulic fracturing, I think, is that it's a continuous process, that it kind of goes on continuously. What it actually is that after a well has been drilled, it is then hydraulically fracked. Typically that takes place over the course of a few days, maybe a couple of weeks. And from that point on, the well produces hydrocarbons conventionally, much like any other oil and gas well.
It feels like a slightly abstract idea, even though you've just described exactly what happens. But what are the dimensions of the areas in the ground that are being fracked?
Typically, horizontal drilling is used. So this is where the well is drilled vertically down from the surface. But once it hits the rock stratum of interest, typically sort of 2 to 3 kilometres below the ground, they turn the well horizontally. So they're drilling kind of horizontally through the rock. Now, each horizontal well might run for, let's say, a kilometre, and then along that kilometre length, they'll conduct kind of repeated stages. So you might hear me later in this interview talking about frack stages, and then each individual hydraulic fracture, typically you're looking at maybe 200 metres from the well. So you're kind of overall perhaps looking at a zone of rock that is maybe a kilometre long along the length of this well bore, stretching 200 metres from either side of this well bore, which is the length of the hydraulic fractures. They're usually longer than they are high, so maybe 100 metres or so above and below the well, and as I say, sort of a couple of 100 metres either side of the well.
OK, so that's given me a much better, clearer understanding of the sort of dimensions in the ground that fracking affects in one bore. So how does it cause tremors?
So the easiest way to actually explain this is with the little practical demonstration that your listeners can do. If you hold your hands together as if you were in prayer and squeeze them hard together, and then try and slide your hands past each other. Now, the friction from pushing your hands together means it's very hard for you to actually slide your hands past each other. Now do the same thing, but hold your hands together very loosely. The friction is much lower, and so the hands are able to slide past each other. That sliding past each other is what we call, when it happens in rocks along a fault, is what we call an earthquake. That is the slip along the fault, that's the rupture, that is what generates the seismicity. So the effect of fracturing is effectively, as the way I've described it, is the difference between squeezing your hands together tightly and squeezing them together loosely. So if you have a particular fault in the subsurface, there are pre-existing tectonic stresses acting on that fault. These aren't faults that are created by the fracturing. These are faults that are already there in the ground, and there's existing tectonic stresses acting on them. And the pressure from the hydraulic fracturing fluid, so you're injecting that pressurized fluid into the ground, if that pressurized fluid goes into the fault, it kind of pushes the surfaces of the fault apart from each other slightly. So rather than being tightly squeezed together in my first demonstration, they're now more loosely pressed together, as in my second demonstration. And that means that the same tectonic force, that same side-to-side pushing, whereas before when the fault was tightly squeezed, the fault wasn't able to slip, now it is able to slip, and that is what generates the earthquake. And it should be clear here, that involves any process that involves injecting fluid into the subsurface.
What are the other factors, what are the other tectonic forces at a drill site that might contribute to fracking stimulating a tremor or a seismic event?
For fracking to cause an earthquake, you need to have a pre-existing fault in the ground that is kind of near to its critical stress. So I think that's something that's quite important to stress, is that we're not kind of creating faults and earthquakes from scratch. This is a pre-existing fault that probably would have had an earthquake on it at some point, but that some point is in geological time, because as geologists we kind of refer to millions of years and tens of millions of years. So at some point there probably would have been an earthquake on that fault anyway, but who knows whether it would have been 100 years' time, 1,000 years' time, a million years' time. So that's the first thing. The second part is, what are the pre-existing tectonic stresses in the ground? So different parts of the Earth, the tectonic stresses are different. It depends on kind of how the continents and the tectonic plates are all kind of grinding and pushing against each other. So it's very dependent on whether or not, and how many, they're never not present, but how many faults are present and what the forces acting on them are.
Presumably there is extremely rigorous assessment of suitable sites before any fracking can take place. But nevertheless, we do get seismic events as a result of fracking. On one site back in August, Preston New Road in Lancashire, there was a 2.9 magnitude event. So how does that transpire once the site has been assessed?
Well, it turns out that it's kind of difficult to see faults in the ground in advance. We use a technique called reflection seismic surveying. And the best way I can explain this is like an ultrasound, but on a giant scale across kilometres. So we use sources, typically trucks that have these kind of vibrating plates on them that send vibrations down into the ground. These vibrations bounce off structures in the subsurface and we record them. And then we process that data to produce much like an ultrasound image, but for the Earth. However, it is actually very difficult to detect. And these are, it should be stressed, smaller faults. So for instance, that 2.9 earthquake at the Preston New Road site, that corresponds to a feature that is maybe 200 metres long. So it's not a very large feature. When you consider this feature is 2.5 kilometres underground, then it's actually quite hard to see these things in the subsurface.
Nevertheless, the UK, we have very strict limits set on fracking, and seismic events above magnitude 0.5 result in fracking being halted. So a 2.9, that's just shut this site down, and that is what's prompted the moratorium that we're now talking about.
Yes, so just to be clear, the traffic light scheme as it's known, whereby you have kind of orange light and red light thresholds where the operator takes action, were deliberately set at a very conservative and cautious level. And the objective of putting the traffic light scheme in place was never that no events would be larger than 0.5 would occur. The actual objective of the regulation was to minimise the number of events that are large enough to be felt by people at the surface and to prevent the possibility of events that were large enough to cause damage or problems for any buildings or infrastructure at the surface.
So what did the Oil and Gas Authority's report actually say about the Preston New Road site?
The first thing that actually needs to be made clear is that the recent reports that were published, of which I was a co-author among other scientists, was entirely focusing on the hydraulic fracturing that took place in November, December 2018. So that was the Preston New Road 1 well. So most of the studies to do with the Preston Node 2 well are actually still ongoing. The number 2 well was the one that caused the 2.9. During Preston New Road 1, we had a 1.5 earthquake. There were reports of it being felt by a few people very close to the site, but it was kind of very much at the limit of what people could feel. So just to go back to that traffic light scheme again, that 0.5 threshold is well below what you'd feel. A 0.5 event could have occurred right beneath you right now, and you would have no idea it happened. It's far too small to actually feel at the surface from a 0.5 event.
As scientists, we're required not to necessarily have opinions, but simply to provide data. But I'm going to ask you the tricky question here. You're an absolute expert on fracking. Do you think that the moratorium is justifiable? Do you think that there is a place for fracking in UK energy generation going forward?
As I said, the studies from the Preston New Road 2 site, which is where the magnitude 2.9 earthquake happened, the studies on that are still ongoing. I think it's a slightly kind of premature decision to have put this moratorium in place when a lot of the science is still being looked at and worked on. The difficulty we have, obviously, is without any sites to conduct experiments and to study data from it, it's very difficult for us to advance the scientific basis. We obviously do a lot of work out in places like North America, Canada, the USA, where we study some of these impacts. But every geological play, as we refer to them, is unique. So, we really need to understand more about the geology of the UK and the impacts in the UK. There's only so much we can do by studying other sites around the world.
Even though fracking in the UK is at an experiment level and doesn't contribute to our energy generation at the moment, we import gas that is generated by fracking from America and other places.
Yes, and actually something that has gone under the radar a little bit is that hydraulic fracturing is often conducted in the North Sea as well. So whilst hydraulic fracturing onshore in the UK is very much a nascent industry, out in the North Sea, hydraulic fracturing is a common technique used to help extract gas from some of the North Sea reservoirs. It should be noted, I guess, that the current policy decisions that have been made are entirely for onshore extraction only and don't apply in the North Sea. And that obviously what follows from that is it's interesting that in the North Sea we've conducted plenty of hydraulic fracturing without triggering any earthquakes, whereas obviously we have triggered seismicity up in Lancashire. And that's a current area of study.
So given that there is this rigorous assessment of the geology at site, but that seismic events such as what happened in the Preston site, they do occur, should people who live near experimental sites be concerned?
This is an area of work that actually we at Bristol have been doing a lot of studies on in the last few years. When you don't have a lot of data about a site to start with and you're kind of moving into a newish site, so we can compare with America where there's thousands and thousands of wells, so we have a lot of data, it's difficult to kind of make forecasts ahead of time. However, what we are getting much better at is making forecasts in kind of what we call real time. So collecting geophysical data live as hydraulic fracturing proceeds and using that data to make forecasts about the ongoing seismicity. So whilst it's very difficult to make predictions in advance, in real time as fracturing proceeds, we can see what's going on. We can see whether the hydraulic fractures are looking like they're going to intersect a fault or not. We can see whether what we refer to as the microseismic events suggest that a larger event might occur. So in real time, you can make operational decisions to mitigate the induced seismicity.
James Verdon from Bristol University. You can email us, bbcinsightscience@bbc.co.uk.